Today I am going to help you in solving the assignment 1 and assignment 2 problems. So first we need to know what is probability, what is random experiment, what is sample space and events. So an experiment is set of conditions under which behavior of some variable is observed. Suppose you are tossing a coin. So in that you are making an experiment. That tossing a coin is an experiment, and we don't know what should be the outcome, that is whether head will fall or tail will fall. So that is the outcome of the experiment is uncertain. So that is called random experiment. And each tossing, suppose we are tossing one time, tossing two times, each toss of this random experiment is called as trial. And all possible outcomes of a random experiment constitute sample space, and each outcome is called a sample point. Suppose tossing a coin, all possible outcome is that head or tail. So that constitutes the sample space, and the each outcome is that you are tossing. Suppose head is coming, that is sample point. Or suppose you are rolling a die. The sample space is you can get 1, you can get 2, you can get 3 up to 6 like that. And each of the if you get 1, that is one sample point. If you get 2, that is one sample point. And an event is the subset of that sample space. What is probability? Probability is the measure of chance of occurrence of some event. That now coming to the next slide. What is random variable? A random variable is a function that maps each outcome of an experiment over a sample space to a numerical value on the real line. Any function of a random variable is also a random variable. Suppose f is a random variable, then z, that is a function of x, is also a random variable. For example, suppose rainfall is a random variable, then if runoff is a function of rainfall, then runoff is also a random variable. And random variable may be discrete or continuous depending on the nature of the associated sample space. Suppose the value of a rainfall or value of runoff, that is a random variable, and thus value that rainfall take is in nature of is a continuous nature. It can be 11.1, it can be 11.12 like that. So there is a continuous sample space, and random variable associated with a discrete or sample space called discrete random variable. So if the set of values of a random variable can assume are finite and countably infinite, the random variable is said to be discrete random variable. An example of discrete random variable would be the number of rainy days in June at a particular location. In June, number of rainy days, here it is not the value of the rainfall, it is number of rainy days in June. So what is this? So it can take up to 30 days, it can happen up to 30 days, so it is countable. It maximum is 30 days, minimum is 0 days, so it is a countable. That and it cannot take between 0 to 1, like 1.5 or half days, like that cannot happen. So this is a discrete random variable. And if a set of values of a random variable can assume is continuous, that is all possible values within a range of real numbers, then the random variable is known as continuous random variable. An example of continuous random variable is the rainfall depth. Here you can see the rainfall depth at a location is a continuous value. It can assume up to 0 to any value. From 0 to any value. It cannot be negative because rainfall cannot be negative, but it can assume 0 to any value. Okay. Now the question is, how exactly does one determine the probability of an occurrence of an event? In other words, how can the precise numerical value of x can be determined? If PA equal to x and x is between 0 to 1, this probability has to be between 0 to 1. 1 is the event will surely happen, and probability, if the probability is 0, then the happening of the event is not possible. And so there are generally 3 ways to assign probability or interpret probability. One is classical approach, one is frequency approach, and another is subjective approach. So what is classical approach? In classical approach, we assume that all outcomes are equally likely to occur without actual experiments. Thus, if there are n equal likely possible outcomes from a given process, and one of the outcomes occur, and one of the outcome must occur, then the assumptions are that each outcome has a probability of equal occurring, that is 1 by n. N is the total outcome, and one is the some event of that in the sample space, and event A is defined as consisting of m such outcomes, then the probability of A equals to m by n. So another is frequency approach. The frequency interpretation defines an event's probability as the long-term relative frequency of similar events. Like if you are tossing a coin for in classical approach, the one example is, suppose we are tossing a coin, we are saying that probability of head is 0.5 because there are only two possible outcomes, that is head and tail. And what is the probability of head? That is one outcome, that is 1 by 2. Suppose similarly for tail, but in frequency approach, how it can be approached like that? If we are tossing one coin one time, suppose we got head, then we are again tossing it, suppose we got head, then what is the probability of getting head? There are two trials, it, and we are getting two heads, that is we are getting, the probability is getting one, but it is not possible. Suppose we are getting third time, we can get tail. Like that, if we keep tossing it, you can see that probability of getting head converts to 0.5. Similarly, probability of getting tail is also converts to 0.5. And another is subjective approach. Subjective approach is what? That is based on your intuition. Sorry, on based upon is your intuition. So suppose you are waiting, and it can vary person to person. So what this is the downs point of the, and this subjective probability is not dependent in the, is not mathematically calculated, or it doesn't see the data. It just from coming from an intuition of a person or his past experience, and it can vary from person to person. So for example, like that I have said already, there are two possible outcome for a tossing a coin, that is two, head or tail, and since the coin is fair, each one is equally likely to occur, so probability of getting head is half. In frequency approach, like I have said, dividing the tossing the coin 100 times, 1000 times, and 10,000 times. Each time we expect to get a better and better addition to the true probability, that is 0.5. As n approaches infinity, the probability approaches the true probability. In subjective approach, suppose you are waiting, suppose even your friend are waiting to board a train at a station, and you are 80% sure that the train will be late based on your past experience and your intuition. But your friend thinks that there are 70% chance that train will be late. So both the thinking are based on intuition and both are different, and they doesn't consider the observed data. See approach. Suppose here is an example in MATLAB. Here is the example using the coin tossing example we are showing. We are suppose the tail represents 1 and the head represents a number 0, and here we are drawing 100 random number from uniform distribution, and if the number is 0, then we are assigning head, and if the number is 1, then we are assigning tail, and then we are plotting the probability of getting a tail using a scatter plot. So let me run this simulation first. Now we can see that for the probability is dispersed among 0 from 1 for trial less than 10, and as we are going forward with more trials, the probability is converging to 0.5. Similarly, if we increase the number of trials, suppose we have made it 800, and then if we run it, then you can see that the probability of tail is dispersed is like it is varying amount 0.2 to 1. Now as the trial increases, the probability converges near to 0.5. Now you can see that the probability of getting tail, probability of tail is nearly 0.5 and is varying very less, centered around the 0.5.
Now the simulation is complete and we can see that the more we increase the number of trials, the number probability of getting tail almost converges to 0.5. It, it is around 0.5, so it's 0.49, 0.60 like that, 0.51 like that. And if we run the trial for infinite time, then it will be nearly 0.5. So it is not possible to run the trial for infinite time. So from this example we can see the example of frequency approach.
Hello, hello. Hi, good evening. Do you have any problem regarding the assignments? Hello, you are not audible actually. You can type in the chat. Hello. Your internet connection, I think, is very poor.
Hello.
Hello.
Sir.
Do you have any problem regarding
Sir.
assignment 1 and assignment 2?
Hello.
Hello.
Today is the first question.
The network is
Sir.
very poor actually. You can type if you cannot. I am not able to
Yes.
hear you. You can type your problem.
Today is my problem.
Hello. Hello. So what are the axioms of probability? Axioms of probability codifies the interpretation and assignment of probability. So what is axiom 1? Any event A should lie between 0 to 1 in a sample space S. This states that the probabilities are real numbers in the interval from 0 to 1, including the boundary that is 0 and 1. Axiom 2 is the probability of sample space is equal to 1. This states that the sample space as a whole is assigned a probability of 1. Since S contains all possible outcomes, one of these outcomes must always occur. And what is axiom 3? If A and B are mutually exclusive events in S, then P A union of B equal to PA plus PB. What is mutually exclusive event? We are coming later. This states that probability function must be additive, that is, probability of union is the sum of the two probabilities when the two events have no outcome in common. All conclusions drawn on probability theory are either directly or indirectly related to these three axioms. So some important definition. So what is a mutually exclusive or event or a disjoint event? Two events E1 or E2 are called mutually exclusive when none of the outcomes in E1 belongs to E2 or vice versa. This is denoted as E1 intersection E2 equal to null set. That is, there is no common outcome, where phi indicates the null set. And then come collectively exhaustive events. When union of all events, that is E1, E2, like that to up to E1, comprise the whole sample spaces, then E1, E2 are called collectively exhaustive events. However, the intersection of any two events need not be null set. like in this figure, these events are all the events comprise the sample set S. But here you can see that E4 event, E3 event have a common outcome. Like E3 and E2 have a common outcome. And when we combine these two, that is mutually exclusive and collectively exhaustive, then the entire sample space is consists of events that is mutually exclusive, that is they have no common outcomes. In this, like in this figure, E1, E2, E3, E4, E5, E6, they consist of the sample space S, and they do not have any common outcome. So in this case, E1 intersection or EI intersection EJ should be a null set. Then come independent events. Events A and B are said to be independent of each other if the occurrence of A does not depend on whether events B occurs or vice versa. And some elementary properties of probability, addition of probability. Suppose in a given trial, a random event A can occur with probability PA and a random event B can occur with probability PB. If A and B are mutually exclusive, then probability that either event A or event B will occur is PA union B equal to PA plus PB. Why here P minus, and from set formula, I think you all know that we have read that PA union B equal to PA plus PB minus PA intersection B. So why it is not coming here? Because it is exclusively stated that A and B are mutually exclusive. If A and B are mutually exclusive, so there are no common outcomes. So PA intersection B should be equal to 0. That's why it is not coming. Here you can see, suppose in a trial, number of total outcomes are n. If M is the total number of outcomes in favor of event A and MB is the total number of outcomes in support of event B, then, and if they are mutually exclusive, that is A intersection B equal to null set, then PA union B equal to MA plus AB divided by n, total occurrence. So we can divide it by PA by MA by n plus MB by n, that is PA plus PB. And it is applicable for n number of events.
फिजिक्स पेपर मिल रहा है सेकंड इयर में रास्ता హ్యాండ్ రైటింగ్ వేరే కొద్దిగా ఫిజిక్స్ లో ఎర్రోడి సైన్స్
Hello. Hello.
Hello, sir.
Yes. Tell me if you have any problem.
Hello.
Hello.
Good afternoon. Good evening, sir.
Good evening. Where are you from?
Yes, sir.
You are from Andhra.
But internet connection is very slow, sir.
Hello. What?
Internet connection is very slow, sir.
Yes, I can hear you now.
Hello.
I can hear you.
Hello, sir.
Hello.
Hello, sir. Internet connection is very slow, sir.
Yes, I understand. I can hear you. If you can tell me your problem, or you can type in the chat box like I can type.
Today.
Hello.
Oh, okay, sir. Sir, just. Sir.
Hello, Yalla Rao.
Sir, చెప్పండి sir. Hello.
Yes, I can hear. If you have any queries,
Yes, sir.
you can write in the chat box if you have any queries.
Oh, okay, sir.
Okay.
Oh.
Then let me continue with my presentation. So addition of probabilities. Suppose in a given trial, a random event A can occur with probability PA and a random event B can occur with probability PB, and if both A and B are mutually exclusive, then P A intersection B equals to PA plus PB. And from the set theory, maybe you all know that P formula for PA union B equal to PA plus PB minus PA intersection B. But why it is not coming here? Because it is already stated that A and B are mutually exclusive event. So A intersection B equal to 5. Here is a small proof of that. Suppose in a trial number of total outcomes are n, and if MA is the total number of outcomes in favor of event A and MB is the total number of outcomes in support of event B, then and they are mutually exclusive, that is A intersection B equals to 5, then P A union B equals to total occurrence of the both the event is MA plus MB by n. Then if we separate it out, then it is equal to MA by n plus MB by n, that is PA plus PB, and it is applicable for n number of events. Now some other properties are, if two events A and B of a random experiment are not mutually exclusive or they are compatible events, that is they have an intersection, then the probability that either event A or event B will occur is that the formula we all know, P A union B equal to PA plus PB minus P A intersection B, and it is graphically shown here. If it is event A and it is event B, this is the this is the mutual outcome of these both events, that is A intersection B. And then come the multiplication probabilities that is independent of independent events. If two events A and B of a random experiment are independent, then the probability of intersection of events A and B is equal to the product of the individual property. Someone is coming. Hello, Monish. Hello. Monish, if you have any query, you can say, or if your network is not good, you can type in the chat box. Hello, Monish, are you there?
Good evening, sir.
Yes, Monish. Where are you from? Hello.
Hello.
You are not audible actually. You can type in the chat box.
Good evening, sir.
Good evening. Monish. If you have any query, you can type here, or you can say, because sometimes your voice is getting interrupted.
Okay, sir.
Are you typing? You don't have to raise a hand. In the chat box, you can type that. Then message box. If you are joining from laptop, it is on the right side of the screen. Yes, yes, understand. You can type, or you can say, I mean, you can say your queries. You can say your question. You don't have to raise your hand. Monish,
Okay, sir. Okay, sir.
you have any queries? तुम्हारा कोई क्वेश्चन है?
No, sir.
ठीक है.
No, sir. No, sir.
Okay, okay. So multiplication properties of probabilities. If two events A and B of a random experiment are independent, then the probability of intersection of events A and B is equal to the product of the individual probability of occurrence of A and B. So with a small example, it can be proved. Suppose you have two boxes, that is box 1 and box 2, each contain n1 and n2 number of balls. Among the balls, there are m1 red balls in the first box and m2 red balls in the second box. Rest of the balls are black. If you draw one ball from each of the two boxes, then what is the probability that both ball will be red? So here why it is independent? Because let event A represent drawing of a red ball from the first box and event B represent drawing of a red ball from the second box. So probability of getting a red ball from the first box is m1 by n1, and probability of getting one red ball from the second box is m2 by n2, and there will be total n1 into n2 number of possible cases of simultaneous drawing from the each box. What I mean to say that in the first box there are n1 number of balls, and for each n1 number of balls there are n2 n2 combination possible from the second box. So what is the total possible case? That is n1 multiplied by n2. The number of cases favoring red balls being drawn from both boxes will be m1 and n2. If we only consider the red balls, then for m1 red balls in the first box, for each red ball in the first box, there are m2 number of possibilities from the second box. So total number of cases should be m1 into m2. The probability of intersection of events A and B will be m1 by m1 in m2 divided by n1 n2. That is m1 by n1, m2 by n2. That is equal to pa into pb. Now come the dependent events and conditional probability. If event A is said to be dependent on event B, if the probability of occurrence of A depends on whether B took place or not, then the probability of that event A occurred provided that B took place will be denoted by probability of PA upon B, and it is called the conditional probability of event A provided that B had occurred. Hence the probability of the intersection of two events is equal to the product, and it can be also shown with a simple problem example. Suppose a box contains n balls, of which n1 are white, n2 are black. Among the white balls there are k number of balls marked with a star. If one ball is drawn from the box, then what is the probability that the ball is a marked white ball? So the ball being a marked ball, it has to be a white ball. So it is a conditional probability. So let event B represent drawing of a white ball, event A represent drawing of a star marked white ball. So what is the probability of event B? Any one of you? That is n1 by n1 upon n. Why? Because there are n1 number of white balls and total balls are n balls. So the probability of drawing a white ball is n1 upon n, and probability of drawing a white ball given that the probability of drawing a star marked ball given that the ball is white is P A by B equal to K by N1. That is K number of star marked ball are there and N1 number of white ball are there. So that is K upon N1. So the probability of a star marked white ball being drawn is it should be probability of event A intersection probability of event B, probability of a star marked ball intersection probability of a white ball, and that is represented by, that is equal to K by N. K is the star marked ball and N is the total number of ball. Okay, then we can write it as N1 upon N multiply K upon N1, that is P B multiply P A upon B. So what is the formula finally? So conditional probability of event A provided event B has occurred is determined by probability of A upon B equal to probability of A intersection B upon probability of B, and here probability of B cannot be 0. Similarly, conditional probability of event B provided event A has occurred. How it should be event A has occurred. A has occurred is probability of B upon A equal to probability of B intersection A upon probability of A, and probability of A cannot be 0. As P A intersection B is equal to P B intersection A, then P A multiplied by P B upon A equal to P B multiplied by P A upon B. This relationship comes handy many times. And what is total probability theorem? If in here we have considered only occurrence of only one event, uh, for A has occurred, only B event has occurred, but here if we consider multiple events, suppose if event A can be realized only when one of the events, that is B1, B2, B3 up to Bn, which together are mutually exclusive and collectively exhaustive occurs, then the probability of event A can be computed from the formula given by this. Probability of A equal to probability of B1 multiplied probability A upon B1. Hi Atul.
Yes, sir.
Hi. You have
Good
any
evening, sir.
good evening Atul. You have any questions?
No, sir. No, sir.
Okay. Where are you from? Uttarakhand.
No, sir. From Aligarh Muslim University.
Okay, 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 good. So, if you have any question, you can type in the chat box.
Okay, sir.
Right now, I am presenting the slides I have prepared for this session. Okay, you can see it,
Yes,
and
sir.
also it will be uploaded on YouTube. You can see it later, watch it later also.
Okay, sir.
So, what is total probability theorem? If event A can only be realized when one of the events, that is B1, B2, B3, Bn, which together are mutually exclusive and collectively exhaustive occurs, then the probability of event A can be computed using the formula given like probability of A equals to probability of P of B1 into probability of A given B1 plus probability of B2 into multiplied by probability of A given B2, like up to n. How it can be proved? Suppose event A can only occur if one of the dependent events can occur first. That is P equal to, what is the probability of occurring P A, then P equal to P B1 intersection A plus probability of B1 intersection A B2 होगा, that it will be B2. Like that, and then what is then probability of B1 intersection A equals to PA into B1 upon A, that comes from this formula. Like this we can get all this proof here, P equals to this one. So here are some example problems. Suppose in a certain wastewater treatment unit, three main types of problems are encountered. A is the event that sample has biochemical oxygen demand greater than permissible limit. B is the event that the temperature of the sample is higher than the permissible limit. And C is the event that the total suspended solid is higher than the permissible limit. And in this Venn diagram, it is given as A, B, and C. And these are the mutual event that is occurring, means mutual outcomes that is occurring here, that is denoted by 1, 2, 3, 4, 5, 6, 7, and 8 regions. So according to this, the question is framed like that. In the given figure, what does the region 2 indicate? The options are BOD and temperature within permission limit, but TSS is beyond permission limit. So first we have to see the diagram. And this is A equals to BOD is beyond permissible limit, B equals to temperature beyond permissible limit, total suspended sound is beyond permission limit. So what does region 2 represents? This one. So region 2 is the union of region 2 represents what? That BOD is beyond permission limit and the temperature is beyond permission limit, but it doesn't represent that TSS is beyond permission limit. So the answer is B. BOD and temperature beyond permission limit, but TSS is within permissible limit. This one represents the TSS is beyond permissible limit, and complement of this one indicate that the TSS is within permissible limit. So answer is B. So in the given figure, which of the following statement is applicable for region 1 and 3 together? So this one is this is region 1 and 3. So what does 1 represent? 1 represent the TSS temperature and BOD are all beyond permission limit. What does 3 represent? TSS and temperature are beyond permission limit. So what does this both represent? The TSS and temperature are beyond permission limit. So according to the option, C is the option. TSS and temperature beyond permission limit. So Atul, are you there? Hello.
Yes, sir.
So can you answer this
Yes,
question?
sir. I'm there, sir.
Can you answer this question that in the given figure, which of the following statement is applicable to the region 3, 5, 6 and 8? Marked as 3. You can see the slide, right? Hello.
Yes, sir. Yes, sir. I can see it. Yes, sir.
3,
I am able to see it.
yes, 3, 5, 6, 8. These four regions indicate what? According to the given options. The options are TSS and temperature within
Sir,
permissible limit, BOD is within permissible limit, BOD is beyond permissible limit, none of the above. So what is the correct option?
sir, 8 is not there in the Venn diagram, I think.
8 is here, right? You can see that. Let me, yes, this one is 8. You can see my pointer.
Okay, yes, sir. It is outside. Okay, sir.
Hmm.
So for this, the option will be none of the above, I think.
Why? What is 3, 5, 6, 8 represent? First, tell me that. It is A represent the BOD is beyond permissible limit, and what is the A complement
Sir,
represent then? Hello.
yes, sir.
A represents that BOD is beyond permissible limit. Then what does A complement represent?
Yes, sir.
Hmm. What does it represent? A complement?
So A complement with that it is not in the region of BOD.
A complement represents that BOD is within permissible limit, right? Okay, you are not
Yes,
audible. Then
no,
I am.
sir. It is not in the permissible.
A represents that BOD is not in the permissible limit, right? And what is A complement? A bar or A complement represent?
Sir, it is the opposite of that.
Yes, exactly opposite of that. Then that A complement is represented by which areas? 3, 5, 6, 8, right? The text region represent the complement of region A, that is A bar or A complement. You can see the upside, right? Hello. Hello.
Yes, sir.
Can you see the slide? That dashed region represent the complement of region A, right?
Yes, sir.
So this dashed region
Sir,
is
your voice is not audible actually.
oh, my voice is not audible. Maybe network problem is there
Yes, sir.
actually.
It is buffering.
Oh, maybe network problem. Then I am just presenting the slide. It is written in the slide actually. You can see what I am trying to say. So in the given figure, which of the following statement is applicable to the region 3, 5, 6 and 8 together? So 3, 5, 6 and 8 together represent the complement of A. That is represented here by the dashed line. So what is the complement of A and what is A? A is that BOD is beyond permissible limit, and the complement of A should be that BOD is within permissible limit. So the answer is B. BOD is within permissible limit. Now for the given Venn diagram, the probabilities are provided here in this table. For region 1, the probability is 0.04. Like that, probabilities are given. So from that, we have question is like that. What is the probability that BOD, TSS and temperature are all beyond permissible limit? So BOD, temperature and all beyond permissible limit is the common area indicated by region 1. So the probability of region 1 is what? 0.04. It is already given. So the correct answer is 0.04. The second question is, what is the probability that at least two of the three parameters, that is BOD, TSS and temperature, are beyond permissible limit? So at least two means what? Either BOD and TSS, either TSS and temperature, either temperature and BOD, or either all of them together. Because it is said at least. If it is said that exactly two events, that it should be BOD and TSS, and all are in pair. But if as it is asked for the at least two events, we have to consider the three events together also, and it is showed by the dashed line in this figure. So what is the probability? That is P2 union P3 union P4 union P1. That is equal to P2 plus P3 plus P4 plus P1 equal to 0.37. So answer is B. So comes to the second next question. What is the probability that exactly two of the three parameters are beyond permissible? What I have said earlier, that for exactly two we have to consider only region 2, region 4 and region 3. Region 1 will not be considered because they have asked specifically for exactly two of the three parameters. So here answer is P2 union P3 union P4 equal to P2 plus P3 plus P4 equal to 0.32. So the answer is C. Hello, Faizan. Hello. Good evening, Faizan.
Yes, sir.
If you have any question, you can write in the chat box or you can tell me here. If you have any questions regarding assignment 1 and assignment 2. Okay, I suppose you don't have any questions. So I'm proceeding with the problem. So the next example is next problem is no failure operation of a device is determined by trouble-free operation of each of the three major component units. The probabilities of no failure of the units during a certain cycle are PE1 equal to 0.8, PE2 equal to 0.7, PE3 equal to 0.9, where E1, E2 and E3 represents the events of no failure of the three components respectively. Considering the events of failure or no failure of each component is independent events, what is the probability that the device will not fail during operation cycle? So probability that the device will not fail is represented by the intersection of no failure of the three components. Also, failure of the components are independent event because failure or non-failure of each component does not affect the working of other components. Hence, the probability that the device will not fail is probability of E1 intersection probability of E2 intersection probability of E3, because working of the device depend on the working of the component, each individual component. So the probability is equal to PE1 multiplied by PE2 multiplied by PE3, that is equal to 0.504. Then the probability that the device will not fail during a operation cycle is 0.504. So it is very less probability that the device will work. So to get better probability, the manufacturer has to make the device such that the failure of the no failure of the components, probability of no failure of the component increases. Suppose if PE1 equal to 0.99, PE2 equal to 0.99 and PE3 equal to 0.99, then the probability of working of the device increases significantly. That is, suppose this is probability is 0.99 multiplied by 0.99, then the probability will be probability of no failure will be 0.97. So you can see that if we increase the probability of no failure of each component, the probability of working of the device increases significantly from 504 to 0.97. So the device becomes more reliable. Now come the next example. Suppose three shots are fired at a target in succession. The probability of a hit in the first shot is given by P1 equal to 0.3, in the second shot is P2 equal to 0.6, and the third shot P3 equal to 0.8. In case of one hit, the probability of destroying the target is 0.4. In case of two hits, it is 0.7. And in case of three hits, the target will surely get destroyed. That is, probability is given as 1. So what is the probability that the target will be destroyed? So for that, first we have to define the events. First, let A be the event that the target is destroyed. So it is a conditional event which depends upon the occurrence of probability of event B1, which represents one hit, event B2 which represents two hits, and event B3 which represents three hits. And A is the conditional probability of target getting destroyed given that probability either B1 or B2 or B3 has occurred. So what is probability of one hit? Probability of B1 equal to, suppose the first shot hit the target, so it is given as P1, but the second shot and third shot could not hit the target. So what is the probability of not hitting the target? Obviously 1 minus P2 and 1 minus P3. Then we multiply these three, and then then similarly, if the first shot does not hit the target, and the second shot only hit the target, and the third shot also fails to hit the target, it is given by 1 minus P1 P2 1 minus P3. Similarly, for 1 minus P1 1 minus P2 multiplied by P3, so we get 0.332. So probability of two hits similarly given as P1 P2 into 1 minus P3 plus P1 1 minus P2 into P3 plus 1 minus P1 P2 P3 equal to 0.468. And probability of three is that all the three shots hit the target, that is P1 multiplied by P2 multiplied by P3. There are no other possibilities, so it is 0.144. So conditional probability of the target getting destroyed for each case is PA given one shot, that is B1, equal to, as it is given as 0.4, probability of getting the target getting destroyed, that is probability of A given 2 hits, that is B2, equal to 0.7, it is also given, and the probability that the target getting destroyed, that is PA given B3, that is 3 shots hit the target, it is equal to 1. That means the target will surely be destroyed if 3 shots are able to hit the target. So using the total probability theorem, the probability of the target getting destroyed is PA equal to PB1 multiplied by PA upon B1 plus PB2 multiplied by PA upon B2 plus PB3 multiplied by PA upon B3, that is 0.332 into 0.4, 0.462 into 0.7 plus 0.41144 into 1 equal to 0.6044. So the probability that the target will be destroyed is 0.6044.